Okay. Is it visible from the back? It's not very bright. Are you sure you can see it? There are empty seats here. Okay. So the content of today's lecture is about machine learning background. And this is the overview. We are going to look at a lot of concepts. So it's going to be a very dense lecture. But I'm hoping that these concepts are just a refresher for you, not you already know these things. We just remember them, and maybe there are a few new things for you, but maybe not. But as you can see, we will see a lot of concepts today, and so we are going to look at machine learning basics by going over supervised learning. As you know, there are many types of learning: unsupervised, supervised, self-supervised. But the easiest to explain, the most intuitive one, is the supervised one. So we are going to look at the concepts over the supervised learning approach. And this will be the content of today's lecture. So as an example, let's remember linear support vector machine. It is a supervised learning algorithm. It is a linear model. So in terms of model type, it's a linear model. And we can call it a low capacity model because in neural network terminology, it only has one layer, right? It doesn't have depth. As a regularizer, it is using maximum margin idea. It is trying to find a decision boundary that has maximal margin to positive and negative examples. It uses the hinge loss as its loss function. We are going to remember what hinge loss is. It's convex. Its loss function is convex, which is good. And there are different solvers to learn a linear SVM, including gradient descent and other second-order optimization algorithms like VFGS and so on. On the other hand, let's look at a convolutional neural network for image classification. It is, again, a supervised learning algorithm, but this time we are looking at a nonlinear model, and it has very high capacity depending on its depth, number of filters, number of learnable parameters, and so on. It is usually trained using cross-entropy loss. We usually use dropout or other regularization methods different from linear SVM. Its loss function is non-convex as opposed to linear SVM. And we optimize it using stochastic gradient descent methods, SGD, and their adaptable versions like ADAM and so on. So let's start by defining supervised learning. In supervised learning, we are given a data set of inputs and labels. And here input is xi, label is yi. The input lives in the d-dimensional real space. It doesn't have to be, this is just an example. It could be an image, it could be a vector, a table, a sentence. And y is the label. And here, for simplicity, we will look at the binary case. So there will only be -1 and +1 classes. And we have n examples in our supervised data set. The task of supervised learning is to learn a function f that predicts, probably correctly, the label of a previously unseen example. So we are going to see this expression a lot. The f is called the model, x is the input, The model takes the input and produces some prediction, y hat. As you know, it's convention to put the hat when it is an estimational prediction. Okay. So the model estimates or predicts the label, and these are the ground truth labels coming from the data set. The purpose of learning F is to apply it to unseen data. That's the whole point. This is usually called the test set. We call the S as the training set, which I showed in the previous slide. And the lower the error rate on the test set, the more successful a learning algorithm is. Because what we care about is its generalization capability, not the error rate on the training set. Okay? For this reason, we split our data set into usually 3 sets. So if this is our whole data set, let's say, when we are developing a machine learning model, we first split it into training, validation, and test. And on the training set, we train our model, its parameters. We check its performance on the validation set. And once the training is done, once we decide that training is, we can stop training, then we check its performance on the test set. So here, there are some concepts. You know, the model is this function f, input is x, output is y hat, learnable parameters are theta, and the loss function is this L. We are going to use capital L to denote loss function. And then hyperparameters. Could be this lambda, but of course there could be other hyperparameters within F itself. For example, the number of layers that you use is also a hyperparameter. Right? It's a design choice that you make when developing a model. So now let's start looking at model types, their capacity, and the concepts of underfitting, overfitting, and generalization. These are very important concepts. So what is a model? A machine learning model is usually described in terms of how it processes a given example. This process is called the model. For example, if your model takes input x and multiplies it with a vector w, dot product, this is called a linear model for obvious reasons. A well-known machine learning model is linear SVM, and its classification model is as shown here. It is W transpose X. W are the weights of the model, but we also take the sign because we are looking at the binary classification task, +1, -1. So is this model linear or nonlinear? We call it a linear model, but strictly speaking, it's a nonlinear model, but because of the sign, right? But we call it a linear model because this is the part where processes the input, right? But strictly, if you look at this function, it's nonlinear because of the sign. How about this one? It's a polynomial model, let's say. It processes the input x by multiplying it with different weight vectors, w1, w2, w3, or weight scalar weights, but also taking the exponents of the data. So do you think this is a linear model or a nonlinear model? What do you think? Nonlinear? So actually, it is a nonlinear model. It implements a nonlinear decision boundary. It's easy to see, but this one could be a tricky question. Let's look at the nearest neighbor method. You know, the KNN, k is equal to 1. In this method, the model takes input x and returns y I star, where I star is the label of the closest example in the training set. So we search over J, xj is element of the training set. We find the closest one, and this index is the index of the closest example in the training set, and we call it I star, and y I star is the label that we are looking for, right? Okay, so what do you think? Is this a linear model or non-linear model? Linear, non-linear? It's tricky because this model has no parameters. So you cannot, this is not a parametric model. So therefore you cannot say that the model is linear on or non-linear in model parameters because there is no model parameters. But as you said, this model implements a non-decision boundary, non-linear decision boundary, because you know when you take the nearest neighbor as your classification, you tessellate the whole space into Voronoi triangles, and the boundaries are nonlinear. But this is not a, we cannot talk about a linear or nonlinear in terms of its parameters because there is no parameters here. There is no W or theta vector in KNN, in nearest neighbor. Model capacity is informally the ability to learn complicated functions. In supervised classification, higher the capacity, more complicated the decision boundaries are. And statistical learning theory provides quantitative measures for capacity. For example, the VC dimension, Wapnick-Chervonenkins dimension. Let's remember this over a simple example. The VC dimension of a model M is the largest number n such that the model can correctly label arbitrary configurations of n points. If you look at 3 points on a plane, we can see that a line can arbitrarily correctly label arbitrary configurations. This is called shattering. So 3 points can be shattered by a line, but 4 points, some of the combinations are impossible. Some of the combinations are possible. When positives are here, negatives are here, you can draw a boundary between them, but when it's like this XOR problem, it's impossible. So we say that the VC dimension of this linear decision boundary or linear model is 3, not 4. But this is good, but it is for binary classification. Researchers have extended to multi-class, but still this is very hard to measure for complex models. It's a useful concept, but in practice we cannot or we don't use it with, for example, deep neural networks. Here's a question for you. If more capacity means that the model can learn more complicated functions, then we should always look for models with higher capacity in order to perform better. Do you think this is true or false? Okay, mostly false. Anybody for true? No? Okay. A few. So, okay, it's false because what matters for success is the generalization error, not the degree to which you can model the training set. It is the generalization error that matters. And we show this usually, this curve, which you have probably seen before. In the x-axis, we have capacity of the model, and in the y-axis, we have the error on training set or test set. So x-axis is capacity, and as you go from left to right, the capacity increases. This means the number of parameters are increased for your model. It could be the number of layers, number of filters, number of neurons, and so on. And error is the error the model makes in classification, or its loss function. If you train your model properly, then you get something like this blue curve. This blue curve is this one, is the curve, training loss curve for your model on the training set. But what you usually get for the test set is this green curve. Up to some point, the test error or the generalization error goes down, and at some certain point, it starts to go up. And we call this the difference between the test error or test loss and training loss as generalization gap. The point where this change starts to happen is you can call it the optimal capacity, and towards the right of it is the overfitting zone. Towards left, it is the underfitting zone. We call this overfitting because our model is doing better on our training set, but worse on the test set. So it's memorizing the training set, right? It's overfitting. I'm sure you have seen this a lot of times, but have you, okay, that question can wait, but let's look at a simple linear regression example. Let's say we are given this 5 or 6 points on a two-dimensional plane. So if you want to fit a function to this, if you want to learn a function to this, you can choose to fit a line, and that line would be like this. But this is called, we can call this underfitting because there is a lot of error here, right? This is an error, this is an error, this is an error, this is an error. So yes, we have a certain degree of error, but the fitting is not that bad. It captures the major trend of the points. If you use the appropriate capacity, and for this specific set, it's maybe the quadratic function, it fits the points nicely, and it also captures the trend nicely. So if an unseen example is later given to us, it would probably be near or on this quadratic, and the error, for example, here, the error of this model will be low. It is low both in training set and the unseen examples. So we call this appropriate capacity. There's also overfitting. Overfitting happens when the training error is very small and maybe zero, but the test error or unseen example error is not zero, it's high. So you can fit a high degree polynomial. It's like this. It fits perfectly your training data, but if I give you an unseen examples from this data generating population, it will probably be from somewhere here. The error of this will be huge, right? So it's a classical overfitting example. Okay, so you probably have seen this many times, but have you seen this before? Double descent phenomenon. How many of you have seen this double descent? A few, okay, 3, 4, that's good. So it's also, that means most of the class, this is something new. So what we have discussed so far is actually this part, right? And this is what classical statistical learning theory tells us. The relation between risk, they call it empirical risk, but loss on a data set, and the capacity of your model. So we talked about this here, but what's happening with deep neural nets is something else. Actually more, not something else, but this of course happens, but there's also this part. That's called the double descent. So let's look at this curve in detail. Again, in the x-axis, we have the capacity of our model. Think of it like your depth, number of parameters, things like that. You increase the capacity of your model. The training risk, which means the loss on your training set, goes down, as usual. And then it hits 0. That means your model can perfectly fit your training set. And when that happens, this is called the interpolation threshold. And as you increase the capacity of your model beyond that point, I mean this part, this phenomena says that the test error will start to go down, and it will probably reach at a level which is probably smaller than what you get with the optimal capacity in the classical sense. What is important here is this point, and from to the left of this point is called the under-parameterized regime, let's say, and to the right it's the over-parameterized regime. So, summary: this is not a theory. This is not a theory, but this double descent phenomena says that if your model is over-parameterized, which means the number of parameters that you learn in your model is larger than your training examples. What does the classical learning theory tell us? Don't do it, right? Because it will overfit, it will just give you nonsense models, but it's not happening with deep neural networks. If it's over-parameterized, then it says that you will get a better test error. So this is very surprising. This is surprising and interesting. I will show you an example, not even with deep models, but very simple, with a very simple model and a simple function. Well, the function is not simple, but look at this function. Y is 2 times something of x. Let's sample randomly 12 points from this function, and we get this data on the top left. These red points are our 12 random points from the function that is shown. The function is probably, I didn't plot it, but something like this, right? You can see the trend. Okay, now let's train a single hidden layer neural network. Nothing fancy. Input layer, output layer, and there's only a single hidden layer. So it's a one hidden layer multi-layer perceptron. And let's train this network on these 12 points. Input is X, output is Y. So scalar input, scalar output. It's a very simple modeling problem. And you can throw a single hidden layer neural network on this. And when you set the number of learning parameters to 31, you get this nice blue trend. It captures the sudden increase at the beginning and then the slow increase in the second part of the points. But this is still can be considered underfitting because we still have lots of errors here, right? Let's increase the number of learning parameters to 2.4K. What will happen? 2.4K is much larger than 12. So we are now, capacity is high. We are now seeing the overfitting phenomenon here because the training error is 0 because it perfectly fits the data, but things in between, for example, here, you see the wiggles, right? You see oscillations. This is because of the high number of parameters. And this is not good. If you sample another point from the same function, the error will be high because of these oscillations in between. Okay? Now what will happen if I increase the number of learnable parameters to, let's say, 10,000? What do you think? So increase it more to 10,000. Okay. Wiggles will be smoothed out, he says. What do you think? So if you look at the statistical learning theory, it will predict that you will get even more oscillations, right? It will be even more bursts. It will still have zero training error, but it will have lots of oscillations, so the test error on unseen examples will be very bad. But it doesn't happen. With 12K parameters, it fits perfectly, and it also smooths out, and it captures the trend perfectly. So the test error of this is also small. So here you see the so 2.4K for this specific problem is where, remember the double descent phenomena, it will be like this. So that 2.4K is somewhere here because the test error is high, training error is low, but the model with the 10,000, 12,000 parameters is here. So it's a very interesting phenomenon, as you can see. And researchers are trying to understand why this is happening. And the most plausible explanation right now is the method that we use to fit these functions, which is gradient descent or stochastic gradient descent. That method, gradient descent, stochastic gradient descent, has an implicit bias. It prefers solutions that have minimum norm, small norm. So when you use 12,000 parameters to fit 12 points, you can imagine that there are many solutions that fit the data perfectly well, right? Because there are too many parameters. There will be many solutions that are equal in terms of their empirical risk. That means they fit the training data perfectly well, zero error. But which one should be chosen is the question. And gradient descent, stochastic gradient descent, has this implicit bias that it's going to choose minimum norm solution. And this minimum norm solution is the solution that is smooth. So it's a nice property of our learning algorithms. So should we always see for the descent? Yes, the current practice says so. Yes. So even if you have a small set, this is not a theory, but this double descent says that you can increase the capacity of your model. This is happening with image data sets and lots of other data sets, but we will see if it holds true for the physics data sets. Or parameter K parameters, we see oscillation. If you increase the parameter size, we have we see more frequent oscillation, but smaller amplitude. So it looks like perfect, but shouldn't be have still many oscillation, but it's small, so it's seen. That's an interesting way to look at it. You are saying that maybe there are infinitely many oscillations, but they are so small in magnitude, they look smoothed out. Maybe. I don't know how to prove it or disprove it. Yeah. But also, I believe because there will be beyond the borders of training data. That's a very interesting question, question, yes. And so your friend is actually saying the behavior of the curve here and here, outside of the domain of our support set, of our training set, right? And this is called out of distribution modeling. And this is a huge problem in today's machine learning, as I also said in the first week. So out of distribution detection, out of distribution modeling is still a problem. So I think my prediction for this problem is this is going to continue smoothly and also this smoothly. So I believe for this problem, the 12K model will generalize better to out of domain, but this one probably not the 2.4 because we see wiggles here. It will probably wiggle here too. But that's definitely an interesting research topic out of distribution. Okay. So interesting phenomena, double descent. Let's look at now the loss functions. And as you might know, there are many loss functions. 0,1 loss function, L2 loss function, L1 loss function, hinge loss, log loss, cross entropy, and so on. There are many loss functions. And we use them to minimize it so that we find the optimal values for the model parameters. So the loss function measures how well our prediction is, and we usually express it like this with the ground truth label and the predicted label. Of course, the lower, the better. And remember what y hat was? It's the output of the model on a specific input, parameterized with the model parameters. And we almost always look at an aggregate loss on a training set, not just individual losses. So you compute this over your training set, and then you basically take a sum, usually, or an average, which are in theory the same, right? You can also make this an average. If you train it properly, they will converge to the same solution. So let's consider an example. Suppose our classification model is this, which is the simple linear classifier. It's W transpose X and then the sign. So if the W transpose X is positive, then this input is classified as a positive example. If that returns negative, because of the sign function, it will be classified as in the -1 class, negative class. So we want our model to perform well on the train set S. That means we want to minimize this loss. So try to understand this expression. It's a sum over training examples. There are n of them. And I here is the indicator function, which means if the mathematical expression here is true, it returns 1. If it's false, it returns 0. And what does that expression say? The model's output, which is the predicted class, is not equal to yi, which is the ground truth label. If they are not equal, then this is an error. And we just count the number of errors on the training set. So I indicator function. So this is the simplest loss. We count the wrong predictions, and that's it. That's why we call it the 0,1 loss. Here we are going to introduce an auxiliary variable z, which is, let's say, zi for ith example. We are going to multiply the ground truth label with the output of the function. Remember, we are looking at the binary classification here. So these are -1, +1, and f is also -1, +1 because of the sign function. So if for a positive example, the model returns a positive value, then multiplication is positive, which is good. Zi means it's 1. But if there's an error, either of the y or f will be positive or negative, so their signs will be different. So this will be an error, which means, so if zi is less than 0, then this is an error, right? Otherwise, it's not an error. So it's just a different way of expressing this part in a more elegant way. And we are doing this because we will use the z function to plot the loss function itself. So as a function of that z. So for example, 0, 1 loss will be plotted as this. Because if z is positive, then no loss is incurred. So there is no, so this part, 0 loss, so no penalty. But here, z less than 0, you have a constant loss. So that's why we are using this auxiliary variable z or z, I don't know. So that means we can write this 0, 1 loss summed over the data set equally using this expression. So indicator function zi less than or equal to 0 is equivalent to this, you know, where z is, as I said before. We introduced this because we will look at other loss functions, and it will make it much easier to see the relation between them through the z function, z variable. To perform well on the training set S, we should search for a W that minimizes this loss on the training set, right? However, we do not use this loss function in practice to train our models. So we usually do not use this to train our models. And does anybody know why? Why don't we use this to train our models?
It's only taking sign, so the difference is not obvious.
Okay. Okay.
We need to take the differential of loss function.
Yes.
We can take the
Yes. I was looking for this answer, but that answer is also makes sense. As I said, if you plot loss with respect to z, you will get this constant function, piecewise constant function, right? This piecewise constant function, first of all, is not differentiable at this discontinuity. Okay. So here it's not differentiable, and in the places where it is differentiable, it gives you 0 derivative. So you cannot use gradient descent to learn a useful W using this loss function. It doesn't give us any clues on how to update our model parameters. That's why we don't use it in practice. Okay. But for evaluation, of course, on your test set to see how well your model is doing, you can count the number of errors one by one. So 0, 1 loss can be used on the test set for evaluation, but training is, we don't use it. Unless you want to do a random search. So any method other than gradient descent. So let's say you want to search for your parameters using random search, which is very inefficient. But if you want to do it, then you can, of course, use 0, 1 loss. It's a valid loss function. Let's look at L2 loss. Again, using the Z formulation, it's 1 minus Zi, because when the model makes a correct prediction, it returns 1, right? And when it returns 1 here, you get 0 loss. Otherwise, you get some loss. And again, if we plot loss versus V, you will get something like this, right? Is that correct? Um, hmm? It should be? Yes, it would be shifted to here, right? Yeah, it would be shifted, but the shape will be a quadratic because of the, yes, it will be like that. So we do not use this with classification, but this is commonly used in regression when you want to predict a continuous value. Yes, this is a very widely used valid loss function. Let's look at hinge loss. It's max over 0, 1 minus Zi. It looks complicated at first, but think of the function z again. If you have a value that is larger than 1, this part will be negative, and this part will take the maximum, and it will return a 0 loss. But if Zi is less than 1 or negative, this part will be maximal, and it will return a loss, a positive loss. Support vector machines use this, and if you plot it, it will be like this. This is 1. So if it's larger than 1, you have 0 loss, but if it's less than 1, you get this linear line. So as you go away from 1, you have larger loss. ReLU activation functions also use this hinge function, and this is a tight upper bound on the 0-1 loss. Remember 0-1 loss? It was this this curve, right? It's a tight convex upper bound on the 0-1 loss. So that's why we love hinge loss. It makes sense. It's convex, and it's also a tight upper bound on the 0-1 loss, which is nice. Yeah, when Zi is linear in model parameters, then hinge loss is convex in model parameters, which is good. We are going to talk about this. And it's a tight convex upper bound on 0-1 loss. Okay, let's look at logistic loss and then cross entropy. So let's look at logistic loss, and then we'll start cross entropy in the second hour. This is also convex, and if I, let's see if I can draw this. So loss, it looks like the hinge loss, but it's a smooth version of it. So it comes like this, goes like that. So this is the log loss. If you plot this expression, you will get that green curve. Again, as the auxiliary variable z has a large value, you have 0 loss, but as it's towards negative, you get a higher and higher loss. This is also convex, as you can see from its shape. Okay, so before we start cross entropy, let's take a 10-minute break or 14-minute break. Okay, we were looking at loss functions, and this is the most widely used loss, cross entropy. So to explain cross entropy, let's look at a multi-class classification case. So we looked at binary class so far, but for cross entropy, let's say we have two discrete probability distributions, P and Q. Think of P as a true distribution. And for example, if you are solving a three-class classification, you are given an image of an animal. You want to categorize it into cat, dog versus bird, cat or dog or bird. Let's say three classes. For example, P could be something like this, where this is 1, 0, 0, which we call the one-hot vector, but it's still a valid probability distribution. If you sum the elements to, they sum to 1, and they are all positive. And Q will be your model prediction. Again, it's a discrete probability distribution. They sum to 1 and all positive. Once you have these two discrete probability distributions, P and Q, how do you measure the discrepancy between them? Because what we want is the prediction Q to be as close as possible to the true distribution P, which is the label in this case. So let's call this label and Q as the prediction. Okay, as you know from information theory, there is this Kullback-Leibler divergence, which measures the statistical distance between two distributions. And KL divergence between P and Q is written like this. It's not symmetric, by the way, be careful. And you can expand the log pi, you know, you can make it minus log qi. Now we split up the log fraction into two logs, and then what you get is pi log pi minus pi log qi. And if you look at these two terms, this one, as you will notice, doesn't depend on the model at all. The model, because the model's output is Q, and we don't have Q in this expression. It's all P, which is the true distribution comes from the training set. So it does not play a role in our minimization or optimization. Therefore, we only look at this part. We try to minimize this part, and this is called cross entropy. Pi log qi. Pi is the label for the ith class. Qi is the model prediction probability for the ith class. Okay. So it comes from Kullback-Leibler divergence. Same thing written nicely. Let's look at an example, a cross entropy example. Let's consider there are three classes. A training example is given as a pair of xy. X lives in d-dimensional space. Y, of course, has 3 dimensions. And each element of the y vector can be either 0 or 1 because it's a label, and there are 3 entries. Now, we need to assume a classification model for this. Let's assume each class have a one versus rest, one versus others, or one versus all linear model. That means for each class, we have a linear model like this. X is the common input, but to compute the response or the membership to each class, we multiply X with the weight vector of that class. So WC transpose X. This will give us three scalar values, F1, F2, and F3. And we usually call these as logits. Okay. And note that the logits are unbounded because they are the output of a linear model here. Depending on the weights of W, F1, F2, F3 can be negative, can be positive, they can be very large, very small, right? So it's unbounded. But we need to work with a probability distribution, a discrete probability distribution. So we need to convert these raw unbounded values into a discrete probability distribution. And the answer to that is softmax. We convert these classification scores or logits to probabilities using the softmax normalization. And it's written here, the formula. You apply the exponential function or e to the power fc, and then normalize it by the sum of these exponential functions. So if you apply this, then we now have a discrete probability distribution which is guaranteed to sum to 1. Okay. Now the summation of Qi, or let's use C will be 1. It's a discrete probability distribution. And you write the cross entropy for this problem as this formula, as we show in the previous slide. Here is the label, the correct label, and this is the model prediction in probability for that specific class index. Okay, so this is cross entropy for multi-class classification. Let's look at cross entropy for binary classes, binary classification task. So just for 2 classes. And in this case, if you use the convention in the previous slide, for class 1, we are going to have F1, so W1 transpose X, right? And then Q1, which should be an element in a probability distribution, we use the sigmoid function, to apply onto this one in order to make it between 0 and 1. So sigmoid function squashes its input. So let's say X sigma, it is something like this. It's a smooth function. Whatever X you give it, it could be minus infinity, plus infinity, anything in between, and it gives you a value between 0 and 1. So, and its expression is 1 over 1 plus e to the power minus x. So we apply this to F1. So what we get here is W1 transpose X. Now this is the expression. This is the, when I give an input to this model, Q1, this is the probability, predicted probability for X belonging to that class. And when I write cross entropy for this specific example, I have only 2 classes, YC log QC, right? This is the expression for cross entropy. And let's expand this log Q1. So there's a minus here, minus Y2 log Q2. Because there are only two classes, this one is 1 minus Q1, so that Q1 plus Q2 makes a probability distribution. And this one is also 1 minus Y1 because there are only two classes, and one example cannot belong to both classes. And when we make these substitutions, for an example, let's say that belongs to class 1, this is the label vector, the cross entropy will be like this. Y1 will be 1, Q1 will be log, Q1 minus log 1 plus e to the power y1 tx. And I'd like to bring your attention to this expression. It is the log loss that we have seen, logistic loss or log loss that we have seen in the last slide of the previous lecture. So cross entropy for two classes is equivalent to the logistic loss. Okay. So the same thing written in a better format. There's nothing new in this slide. So, okay. Now we have seen most commonly used loss functions. Let's see. Let's try to name them now. Okay. What is this curve in green? Which loss function is it? L2 loss. This is L2. And the one in blue, hinge, right? Yes, so this is hinge. And then red one, logistic or log loss. And then the black one, yes, this is the 0,1 loss. Okay. Good. Now we will look at the training or learning or fitting concepts related to this topic. And under it, we will look at numerical optimization, and we will discuss concepts such as convexity and the algorithms like gradient descent and its variance. Training is nothing but an optimization problem. We define a cost function or an objective function first on the training set, and then we minimize it. We usually express that optimization problem using this expression, argmin of L. You know what argmin means, right? So if I write, if I don't write arg, what will this give me? The minimal value of the loss function, we call it, let's say, L star. But when you say arg, it gives you the argument that minimizes the thing that you are minimizing. So the output will be theta star. So a central question here is whether the cost function is convex or not. That's a very important question. As we discussed in the last week, you remember we talked about AI winters and summers. One of the AI winters, which means artificial neural networks where people lost interest in them, was because their loss functions were not convex. And the SVM loss function is convex. Because of that reason, almost all researchers, scientists started to use convex loss function models such as linear SVM and abandoned artificial neural networks because it's not good to work with non-convex loss functions. But as we know today, in practice, we optimize them all the time with success. So that was also like the classical statistical learning theory, which told us not to use over-parameterized models. Numerical optimizers, numerical optimization people also told us not to use non-convex loss functions, but we didn't listen to them, and we use them all the time now with success. So convexity is, as you remember from your mathematics classes, a function shown in blue is convex if you take any two functions on it and draw a line. If the function is always below that line, then it's convex. Okay, so simple definition. The convex cost functions are good because we know how to minimize them reliably and efficiently. Because they are like, think of the quadratic function as a typical example of a convex cost function. Wherever you start, if you take the derivative of the cost, it will give you the direction where it decreases. Well, the derivative gives you the direction where it increases, but if you take the minus, it gives you the direction where it decreases. And with methods that find the step size of this step, it gives you the direction, and there are some clever ways to find the optimal step size. You make some iterations and find the global minimum in iterations, many iterations or few iterations. So in that sense, there is no need to provide a good initial point, because wherever you start, you are guaranteed to find the global minimum. And when you minimize the convex cost function, you are sure that you did your best. That's a very nice feeling, okay? Once you minimize it, okay, this is the global minimum. You cannot do better than this. But with non-convex functions, loss functions, you find the local minima, but is it good enough? You are never sure, because the global minima is maybe somewhere else. So that's why people love convex cost functions. Of course, they are good. Yeah, non-convex optimization problem. Reliable and efficient ways of minimizing it, question marks. Although we can now optimize deep neural nets very successfully, it's not because we have very reliable, efficient method, but it's because of lots of trial and error and lots of years of experience, right? We'll talk about those topics. You need to provide a good initial point for the non-convex optimization problem. And when you find the minima, you are never sure whether this is a global minima or a local minima, and whether that local minima that you find is good enough for your purposes, for your task. So that's why people didn't like non-convex functions, understandably, and people liked convex cost functions. So then the question is, if I have a loss function, how do I check whether it's convex or not? Checking convexity is often difficult in high dimensions, right? It's not an easy task. There are a few different methods. First, analytically, you can verify the definition. What was the definition? You take any 2 points, draw a line, and if you can prove that the function always is below that line, then it's convex. But how can you do this with 7 billion parameter neural network? So it's very difficult. If you have a simple model like the 12-point data set I showed you, just one input dimension, then yes, there you can do it. Another method is the twice differentiation method. If the loss function is twice differentiable, then you take its derivative twice. And if the resulting second derivative or Hessian if it's multidimensional. If it is positive or positive semi-definite, then it is convex. But this is also, again, maybe not very easy. Or you can show that the function, the loss function, is obtained from convex functions using convexity preserving operations. So this is, again, like this is a mathematical way of testing convexity. And also, you can always numerically choose a finite support and simulate the loss function in that support and see if it has the convexity properties. This will never give you a 100% proof, but it will give you an idea whether the loss function is convex or not. I'm going to go over them very quickly. So these and upcoming 2 slides are about this part. So what are the convex functions and what are the convexity preserving operations? Because these are all known, right? There are basic functions that such as the affine function ax plus b, exponential function, powers of absolute value, negative entropy, things like this. These are convex. You can prove that they are convex. If your loss function is composed of these functions, then your loss function is guaranteed to be convex. There are also concave counterparts. Norms are also convex. Affine functions are convex. Spectral norm is also convex. And these are the operations that preserve convexity. If you take a non-negative weighted sum of convex things, you still get a convex function. If you compose with affine functions, it is still convex, and so on. So it's not easy. You can see that it's not easy by trying this homework exercise yourself. This is one of the actually easy examples. So you can try that. The logistic loss, remember what was it? Log or ln 1 plus e to the power something like this. So try to prove that this is convex, okay? I'm not going to do it here because of time. So convexity is a big issue. There is a huge literature on numerical optimization, on how to optimize convex functions and non-convex functions. But in this class, we will only look at gradient descent, so-called first-order numerical optimization methods and their variants, although there is a huge literature on numerical optimization. Here is the landscape of all optimization problems, which is called mathematical optimization. Under it, there is this nonlinear optimization, which covers all. This is the largest set. Under it, convex optimization is a smaller subset, and within it, we identify specific optimization problems such as least squares and linear programming. So least squares, as you know, it is this optimization problem, ax minus b. You minimize its norm, well-known problem, lots of applications in engineering and science. We can find analytical solution to it, which is very nice. There's just a formula, you evaluate it, you find the solution. There are good algorithms and software to minimize it. High accuracy, high reliability, and time complexity is good. I'm not going to go into details of it. So we consider this as a mature technology. You can, if you convert your engineering problem to a least squares problem, then you can consider it solved, because least squares is a solved problem. Linear programming, there is no analytical solution as opposed to least squares, but still we have algorithms and software, and they are reliable and efficient, and its time complexity is still manageable. And these are problems in this form. You are minimizing a linear function of x, c transpose x, subject to some linear constraints. This is also considered a mature technology. Linear programming optimization problems are solvable with reliable and efficient guarantees. A larger set is the convex optimization, which is in this form. It's the now more general than least squares and LP. Again, no analytical solution, but there are algorithms and software to solve these problems, reliable and efficient. Time complexity is, of course, higher than the previous ones. This is almost a technology. So convex optimization is if you can convert your engineering or science problem into a convex optimization problem, then you can consider that it can be solved. What about nonlinear optimization? We are in this region with deep neural networks. Sadly, no effective methods to solve. Only approaches with some compromise, local optimization, and this is more art than technology. I agree with this 100%. Optimization of deep neural networks is more art than science. Global optimization, there are methods, but like simulated annealing, right? But no guarantees, and efficiency is out of bounds. In practice, you don't use them. You get help from convex optimization in terms of initialization, heuristics, and bounds. And this is considered far from a technology, something to avoid, actually. This is the conclusion of numerical optimization people. And they are right. They have reason to say this because of all these bad properties. But with deep learning models, we minimize non-convex loss functions all the time with success. And again, we do this using first order methods like gradient descent, stochastic gradient descent, and it works. And this is really, this is coming from practice, actually. If you only look at theory, you wouldn't even dare to optimize deep neural network loss functions. But in practice, it works really well because of things like double descent phenomena. Okay, those solvers have some properties which makes the optimization work. And also, so as I said, it's lots of trial and error and years of experience. So let's say I give you a data set and I wanted you to train a neural network on it. What you would do probably is to take a well-known neural network like ResNet and start with a pre-trained one even, and then use the common learning rates that has been known to work. So this is years of experience accumulated there. If you did not have any clues on about the ResNet and the learning rate ranges that work, then you would have to make lots of trial and error because not all learning rates work. You know that. So yes, we are able to optimize them using gradient descent, but it took lots of trial and error and years of experience with hundreds or thousands of researchers working together. Now we know how to minimize them. Still, it's not guaranteed, right? If you don't do the hyperparameter tuning well, learning rate, batch size, and other things, you can get a bad test error. So it is still something that we need to figure out, the optimization of neural networks. And it's an active research topic. It's very hot research topic, actually. Okay, let's look at the champion of this optimization challenge, which is gradient descent. We use it all the time. The goal is to minimize the cost function L. We compute the gradient of L with respect to model parameters W, which is this. Remember, gradient is the vector of partial derivatives of a multivariate function. And this gives you, what is gradient give you? What does gradient give you? Or what is a derivative?
The direction that you go. Inside of. So,
Yes. So
It's the direction of the steepest descent.
steepest ascent. Derivative. Derivative is the direction of steepest increase at a point, right? And this is direction of increase with respect to all the variables. And if you use the minus of this, the other direction, this gives you the direction of the steepest decrease. Now you know the direction, you need to take a step in that direction and repeat this process many times. This is what gradient descent is. Here you can see its update equation. You take the gradient of loss, multiply it with a step size or learning rate. This is also called learning rate or step size. And of course, negative is very important. If you use positive here, you will maximize your loss, which you don't want to do. And this is how you update your model parameters. How do you find the gradient? Let's refresh our knowledge about this. In one dimension, this is the definition of derivative. It's the limit of the difference of fx plus h minus fx, where h is a small step which goes to 0. This gives you the derivative in one dimension. But this is the analytical definition. In practice on digital computers, what do we do? You can do finite difference methods. You take a step h, subtract that, or subtract fn from that fn plus h, and divide by h. And there are other versions of this too, central difference, for example, or forward difference, backward difference. This is slow, but easy to implement, but approximate. It doesn't give you the exact gradient, right? So it has disadvantages. On the other hand, if you compute the derivative analytically on paper, right? So if your cost function is something like this, you know that the derivative will be 2x. This is the analytical computation. And if you do it on paper and you implement this derivative, then it will be very fast, it will be exact, but it's very error prone to implement. It's very easy for this function, but think of a huge neural network. If you need to write the derivative by hand, good luck with that. It's not easy. But we will see that auto differentiation and chain rule makes it easier. So you find the analytical derivatives of each computational block and then combine them in the proper way. Then you don't have to do this for the whole thing, right? In practice, if you are implementing a loss function yourself, you can do the second way and then implement the first way, which is easy, and check whether they are in accordance. But today, having PyTorch, Keras, TensorFlow, things like that, they have auto differentiation features. You don't have to deal with this by hand, right? But as deep learning researchers and in this class, we are going to do some by hand backpropagation calculations. If your function has multiple variables like this, f of x comma y, then we don't talk about derivatives, we talk about gradients. And gradient is the vector of partial derivatives. So the partial of f with respect to x, partial of f with respect to y. Partial derivative tells you the rate of change along a single dimension at a point. These are all from your calculus classes, quick reminders. And the chain rule, of course, you know from Isaac Newton from the 16th century. And this is the basis for backpropagation. If you consider z to be a function of variable y, which is itself a function of x, then y and z are therefore dependent variables, and so z becomes a function of x as well. And how do you differentiate z with respect to x? You use the chain rule, right? So we use this all the time when you are computing the gradient in a deep neural network, because a deep neural network, as we have seen in the first week, is a model that is functions of functions, right? There's functions of functions. These are linear and nonlinear operations stacked on top of each other. You use the chain rule and you get the whole gradient. An example, let's take the derivative or gradient of hinge loss. This is a little bit tricky because of the max function here. So if you want to minimize this L with respect to W, what you need to do is take the derivative of L with respect to W. Easy, right? But how do you deal with these max? Because max function is actually not differentiable in a strict mathematical sense. So, for example, if you choose f to be x and g to be minus x, so it will be something like this function, x on one side, minus x on the other side, then you have a, so the derivative from the left and from the right will be different, +1, -1. And calculus tells us that if at a point the left derivative and right derivative are different, then this function is not differentiable. So then how does this work? Because ReLU is like this. ReLU is not differentiable at this point. But in practice it works using subgradient or subderivative. So max is not differentiable. We can use subgradient or subderivative, which saves us. And subderivative generalizes the derivative to non-differentiable functions such as max. It's a very easy idea. You see the mathematical definition on the left, but let's look at the figure. Blue function, as you can see, is a piecewise linear function, and it has all these breakage points. It is continuous, but if you look at the derivative, at those points, it's not differentiable because the left derivative and right derivative are different. So what can you do in that case? For example, at this point, x0, subgradient tells us that as a derivative, at that point, you can use one of these slopes, and this is called subgradient. So anything that is under the function can be used. This is called subgradient. And in practice, what do we do? You either use the left derivative or right derivative because both are subgradients. That's it. And this works in practice. Okay. Think of ReLU. At this point, you either use zero derivative coming from the left side or 1, which is the derivative of the right side. Just pick one of them consistently and it should just work. So back to our example, we can write the subgradient of the hinge function. I'm not going to do it step by step, but here is the answer. You take the derivative of this max with respect to W. Of course, it will have two pieces because it's a piecewise function. If HW is in the region where it's positive, you get H derivative, otherwise 0. And this is the result. Okay. You can also try this yourself by hand. It's a nice, simple example. And also, there is a hands-on tutorial on this. I'm not going to go over here, but I posted on the course web page. Just look at it, execute it, and try to understand it. I think it's very useful. Here, I'm just going to quickly skim over it. So it's on week 2. Here, Collab Notebook. So we are looking at a very simple classifier like the hinge loss classifier, but it's actually neural networks are not very different. So this simple Collab notebook actually shows almost all the steps in a neural network development. What is this? Okay. So in this Collab notebook, we are working with 2D data sets, and we first create a simple data set like this, blue and orange points. And then we define our classification model such like this, W transpose X plus B. There's a bias term also. We added this here. An auxiliary function to plot the boundary on data. And this is the classifier. For a given W and B, we just plot it on the function or on the data, and it gives us this decision boundary, which is nice. You can implement the 0-1 loss function, which is just counts the cases where the prediction and the label disagrees. And here you can find a optimizer, which is not gradient descent. This optimizer is random search. For 1,000 iterations, it picks randomly W and B between some bounds. Here you can see plus 0.5, minus 0.5, and so on. And it computes loss and just keeps the parameters that gives the minimum loss over 10,000 random trials. And this itself finds a good boundary, like this is probably optimal boundary. But it works here because this is a very simple problem. In high over-parameterized, high parameter count deep neural networks, random search is not a good idea. You cannot do it. And here starts the hinge loss. This is 0-1. And you see the blue curve is the 0-1 loss. Red one is the hinge loss. It's a tight convex upper bound, which presses that from top. This is hinge loss. Derivative of hinges here, which I showed you in the slides. But in the slides, I didn't show you the B bias term, but here you also have the bias term. So just check how this is implemented and how this plays out. And this is where it is implemented in Python. Okay, and this is the gradient descent part. We compute the gradient, we take a small step in the negative direction, and the gradient was calculated here. And that's it. Okay. Actually, okay, it doesn't show the, but here it shows step by step how the decision boundary moves to its optimal location. So just execute this and go over it. It's a nice demo. Okay, we have some few topics left, but let's take a break at this point, a 15-minute break, and then we'll come back. Okay, gradient descent, but an important point is how to set the learning rate. What is that, the value of eta? And for that, numerical optimization literature actually provides answers, many answers and algorithms. For example, the Newton's method, BFGS, limited memory BFGS, line search, Wolfe conditions, etc. These are all methods that also gives you the step size, but a common nullity of these methods is that they are second order. They need the Hessian matrix, they need the second derivative. And the problem with that is if you want to optimize a neural network with billions of parameters, computing the second derivative or the Hessian is not doable. So let's say 7 billion parameter neural network, the Hessian will be 7 billion times 7 billion matrix, which probably don't fit the GPU memory. So therefore, we cannot use these nice algorithms, these second order methods, and all we can do is the gradient descent, which is a first order method. We will study the most basic methods and some adaptive ones of it. Stochastic gradient descent, SGD with momentum, ADAM. ADAM W is a new version of ADAM, RMS prop, and so on. So we are going to look at these things. In a nutshell, gradient versus stochastic gradient, the difference between them is very simple, easy to understand. Here is the our loss function, L. If we calculate its gradient, it's this, right? It's again 1 over n summation derivative of loss with respect to W. And this is the whole gradient that is calculated over the whole data set and examples. Stochastic gradient, on the other hand, is you can calculate it on just one example that is randomly chosen from the data set. That is called stochastic gradient descent. You choose one example from the data set randomly and compute this gradient on that example, and this is called stochastic gradient. Or you can do a group of examples that are randomly chosen, and we usually call them as the batch, mini batch, right? You choose a mini batch randomly and then calculate the gradients on that examples only. And that's it. This is stochastic gradient. Okay. And how to set the learning rate? It's empirical. It's trial and error. You need to tune it by a grid search. There are adaptive learning rate methods such as ADAM. There are learning rate scheduling methods such as cosine annealing. Many different algorithms, but still you have to look for which one is working the best, and you have to search for the at least the initial learning rate if you are using a scheduler. So it is still a trial and error type of thing. So there are some theoretical results on why stochastic gradient works. This is from 1998. When you decrease the learning rate with an appropriate rate, this is a learning rate scheduling, a type of learning rate scheduling, stochastic gradient descent converges almost surely to a global minimum when the objective function is convex or pseudo-convex. Otherwise, it converges almost surely to a local minimum. So these are good properties of stochastic gradient descent. So with a non-convex loss function in neural networks, we know that we are converging to a local minimum, but then how come we get good results, good generalization out of it? This is really a research question. But the short answer as a summary is in over-parameterized models with lots of parameters, there are a large number of local minimas that are equally as good as the global minima. That's you find one of the local minimas, and that's good. And gradient descent converges that model to a local minima. When you stop stochastic gradient descent, you can choose to monitor the training loss. When the change in loss becomes small, that means training loss becomes flat. Change in model parameters becomes small. You monitor the change in network weights, iteration by iteration. If it becomes small, you can stop. Or you might have a separate validation set on which you monitor the loss. If it does not improve, you stop. Or you might have a time budget or max iteration count, depending on your context. Then you can stop SGD based on that. Okay, that was all about the training, numerical optimization, gradient descent, and so on. Let's briefly look at regularization. It is a way of controlling the capacity of a learning model. Remember, capacity is, there are theoretical measures such as VC dimension, but they don't work for highly parameterized models. And what we use as a proxy to capacity is the number of parameters. Number of learnable parameters is a good proxy measure for the capacity of a learning model. Intuitively, regularization favors simpler, lower capacity models. And this is the famous Occam's razor principle, which says that among competing hypotheses, the one with the fewest assumption should be selected. Or if two different models explains the data equally well, choose the simpler one. Remember the 12-point data set I showed? For that 12 data points, 12,000 parameters gave a good, smooth result. And with 12,000 parameters, you can find many different models that has exactly zero training loss. You have to choose among them. And Occam's razor principle says that choose the one that is the simplest. How do you quantify simple? You have to choose something. And in that case, it's the norm of the solution. If you choose the minimum norm solution, you get that nice smooth curve. We can also explain this over well-known support vector machine because as a regularizer there, they use margin maximization. So let's talk about it. In linear SVM, suppose we have two classes, black circles and white circles, and this is a linearly separable data. So you can find linear decision boundaries that perfectly separate these two classes. And the problem is there are many of them, right? This line also has zero training loss. This also, that one also. There are infinitely many decision boundaries that gives you zero training error or loss. Which one should you choose? That's the question. And if you remember the loss function of linear SVM, can you write it from your memory? So this is the loss function of linear SVM. This part is hinge loss. and it measures the empirical risk, right? How many data points are violating this hinge loss, and we are trying to minimize it. What about this part? What does this do? Yes, that's the regularization part. Why? Because if you look at the geometry of linear support vector machines, the margin between, so if I give you a line, the closest distance to that line to the, for example, white and black points is given by 2 over norm of W. This is coming from geometry. And since this is called margin, right? It's the separation between examples. And if you want to maximize this margin, you want to minimize the norm of W, because that margin is given by 2 over norm of W. So I want to minimize the norm of W. That's why this term is there. You are trying to minimize the norm of W in your loss function. So this one is the regularizer, which maximizes margin. So if you don't have that term, suppose that you don't have this term, the support vector machine will still work, and it actually corresponds to the hinge loss classifier that I showed you in the Colab notebook. You can go there and execute it. It will find you a decision boundary that is good enough because it will have zero training error, but it might find you something like this. And its generalization error might not be that good. But when you introduce the regularizer, it will find you the best one that is right at the middle of positive and negative examples. And in that Colab notebook, I think it is either given as exercise, I forgot, or maybe there is an example of that regularizer there. You can try to implement it yourself. So other most commonly used regularizers are L2 norm and L1 norm because we want to minimize the norm of the solution to favor simpler solutions. Although there is research against simplicity bias. So there is research saying that preferring simplicity always is not good. We can maybe talk about it later. But common practice is you use L2 norm on your parameters or L1 norm. If you use L1 norm, it enforces sparsity, your sum of your weights. It tries to make as many of them as 0. So it tries to make it sparse. There are also algorithms like dropout for regularization. It randomly kills some of your neurons in the network during training. And by doing that, the network gains some robustness because it cannot rely on all the neurons being there all the time. So it randomly you kill some of the neurons, so it brings a robustness and regularizes the network. Data augmentation is another regularization. If for image classification, you add noise, you flip the image, you rotate it slightly, right? You translate it. These are things that regularize the model and you get a better generalization accuracy. Okay. Let me know if you have any questions, okay? Anytime, please ask.
You stochastic gradient descents, are we choosing completely random or are there some persons what we do?
That's a good question. In stochastic gradient descent, in the plain version, it's totally random. But there are methods, for example, in imbalanced data sets, when you are forming the batches, you want to favor rare classes more. So it's called random oversampling. So when you form a batch, you put more from the rare classes in a batch. So yes, there are methods to do that. But mostly it's pure random. But you can do oversampling from some classes, undersampling from other classes. So let's talk about the distinction between parameter and hyperparameter. Are they different? They are different. And in linear SVM cost function, this is a learnable parameter because it's the model, it's a model parameter, right? What is the model? Model is here. It is the process that processes the input data. So W is a model parameter. And what is a hyperparameter here? C is a hyperparameter. It is a weight variable which balances two losses. One of them is the regularizer, the other is the loss that minimizes training loss. So C trades off between those two. So W is a model parameter. It is learned on the training set, right? This process is called learning or training. And we use numerical optimization methods such as stochastic gradient descent to find the optimal value of W. On the other hand, for hyperparameters, for example, C, this is learned or searched on the validation set, right? So these are the distinctions, fundamental distinctions. And this process is called model selection or tuning. We don't call this, well, you can call this training, but it has a specific name, model selection. And there are search algorithms to do that. For example, grid search is the most widely used one, but there's also Bayesian search. And there are computational libraries, packages that does this for you. For example, weights and biases, hyperopt, raytune, etc. So this is the distinction between parameter and hyperparameter. A question, can't we use the training set for finding the best value of C? Why are we using the validation set to find the value of C? What do you think? So what would happen if you use the training set to find the value of C? Okay, C will be overfitted to the training set. But C is just a scalar, just one number. What does it mean to overfit? Yes. Yes, exactly. That's the answer. So if you try to optimize C on the training set, an obvious optimizer is C, setting C is equal to 0. If I set C is equal to 0, then there is no error in the hinge loss part. And you can set all the W to 0 as well. It's minimized, right? But this doesn't work. C, we find the value of C on a separate data set so that this degenerate solution is avoided. Okay, and this is called model selection. So you are choosing, so model selection may mean two things. You can choose a model among different models. For example, K nearest neighbor, logistic regression, decision tree, ResNet, transformer. And it also means that you choose a model from the same family with different hyperparameters. This is the choice of C that we made. So this is also called model selection. Hyperparameters can be model related or optimization related. We have two types of hyperparameters. Model related ones are, for example, C in SVM because it appears in the loss function or the objective function. But other ones are, for example, number of layers in a neural network is also a hyperparameter. Nobody tells you how many layers to use. You have to choose it. You have to design this network, right? You have to search for it. It could also be learning method related. Learning rate, schedule, and batch size are also hyperparameter that needs to be tuned. Cross-validation is a widely used method to achieve both of these things because there is a separate validation set. Okay, last two topics. This was a dense lecture today, but when we do this, that will be over. So there are two estimation methods in machine learning that are widely used. One of them is maximum likelihood estimation, which we do all the time. And there is also maximum a posteriori estimation. Let's look at what they mean. In maximum, so both of them are methods to estimate the parameters of an assumed probability model. That means, suppose that we are given a set consisting of n data points. And here, for simplicity, I just show an unsupervised data set. So there is no labels here, but you can also do this for the label too. It will just work. So you are given a data set, and we have a model parameterized by theta, a probability model, which measures the probability of the samples. And the problem is here how to estimate this parameter. And maximum likelihood and map have different philosophies to approach this problem. Let's look at the maximum likelihood first. In maximum likelihood, you want to maximize, so we want to find the optimal parameter, argmax, search over theta, and probability of data given the parameter. So now this is like an abuse of notation because this probability, this one is not defined on a set of examples, but rather it's defined on just individual examples. But so that's why this one is, it's an abuse of notation, but it shows the intuition behind it. So we are trying to increase the likelihood of data under this parametric model. But in order to work with this, we need to make an assumption, IID assumption, independent, identically distributed. If my examples in dataset S, if I assume that they are independent and identically distributed, then I can write this probability as a product over all examples because they are independent. So xi theta. Okay. And when you work with this, this is called maximum likelihood. You can take the log of this, and the product becomes sum, and this becomes maximum log likelihood, and it's the same thing, except the one with the log is easy to work with because it's a sum. But working with a product is not easy. So that's it. This is maximum likelihood estimation. And cross entropy, you can derive cross entropy actually from the maximum likelihood estimation. Maybe we will do it in the next week. But yes, this is the same thing. I wrote it before, copy pasted here. This is the maximum likelihood estimation, and working with the log is more convenient, and you either write this maximum log likelihood or more conventionally, because we try to minimize things in numerical optimization, we take the negative of this, and this is called the negative log likelihood minimization. So if you further take this a few more steps for example, multi-class classification data set, you will arrive at cross-entropy loss. Okay, we will do it. So cross-entropy loss is actually doing maximum likelihood estimation. What about map? There is a nuance there. So in map, we start with this optimization problem. Remember, in ML, it was the other way around. We tried to maximize the probability of S, the data. But now we maximize the probability of data. That's the only difference. So it's a philosophical difference of approaches. So you, using the Bayes theorem, you write this expanded, you can write it like this. In the denominator, you have probability of data. It is constant and can be ignored. And then at the end, you arrive at this one, which is similar to maximum likelihood. In fact, the first part, the first term is the maximum likelihood itself exactly. But there is an addition, which is log of probability of theta. This is an extra term that defines a prior distribution on the parameter theta. Okay, so that's the only difference. So if we compare and contrast the two, on top you see the maximum likelihood. Below that it's the maximum a posteriori estimation, and the only difference is that one. So ML estimation is equivalent to map when the prior on the parameter is uniform. So if you assume a uniform prior on your model parameters, then both of them would be the same. Okay. Yes.
Is this maximum likelihood and about one of the discriminative?
No, no, it's not. So here I said you start with a set of examples, but this can be only data examples, no labels, or you can. These can also be tuples of x and y's. So it's not related to supervised or unsupervised learning. It is, these two approaches are two ways of finding the theta when you assume a probabilistic model. You can apply it to unsupervised and supervised settings. And generative and discriminative as well. I think that's all for today. If you have any questions, we can stay and discuss if we have some time. But otherwise, see you next week. İyi de,